Hey guys, all right, this is gonna be our introduction to automotive electrical. All right, first thing, a couple things we gotta cover, some definitions on automotive electrical stuff. So there's three things that we can measure. There's more than this. This is probably an oversimplified version. I'll bring you guys a little closer. There's three things that we're gonna be able to measure consistently when testing out electrical issues in our vehicle. So my main purpose of this is to identify electrical problems, where they are, so we can then fix them. I'm not going to get into electrical theory. I'll touch a little bit on it to help explain it, but that's not going to be a heavy part of this course. So we have voltage, all right? We have current, and we have resistance. These are the three things we're going to be able to measure in a circuit to determine where, all right, to help us identify a problem. Voltage is defined as electrical pressure. All right. Voltage is what's pushing electrons down the wire and going through anything that requires it to be turned on or light up or a motor to spin or anything like that. So voltage is the thing that's pushing the electrons down that wire. All right. The symbol is either V for volts or E. You'll see it in E. If you get some older textbooks, before we really defined all this stuff, it was known as electromotive force, and so that's where the E comes in. Anyway, the symbol is either V or E when you're looking at stuff, and the units of voltage is the volt, 1 volt, or how many volts, number of volts we have. All right. Current is the flow of electrons. All right. Current is actually what goes through a light that causes the light to light up. Current is what goes through the motor to cause the motor to spin, or a fan to spin, or anything like that. So current, and I'll get into a little example about that. The symbol for current is either I or A, all right? And the unit for current is amps. So the A comes from amps. I, again, it goes back to an older, 75 years ago, they called current intensity, because if you had more electrons going through a fan, that fan would spin faster. Or if you had more current going through a light, that light would shine brighter. So that light was more intense. So that's where the I comes from. And then the last one we're going to cover today is resistance. Resistance is what slows down current. All right? It's typically the thing that consumes some of those electrons and slows them down. All right, so it's the opposite. These two work opposite. All right, if you increase current, resistance has to go down. If you increase resistance, less electrons can flow through, so current goes down. The symbol for current is this omega symbol, or the letter R, and we measure resistance in the units of ohms. All right, ohm is a unit of current, of resistance. Amp is a unit of current, and volts is a unit of voltage. So back to current. All right, let me cover some of this. So let's say I have a wire. This is a wire. Inside this wire, I have a ton of electrons. All right, these are all electrons. These electrons are flowing in this direction. All right, so they're coming from a battery over here. They're coming over here. They're going to a light bulb. Now, current is the number of electrons that pass through this line in 1 second. All right, it's the actual number of electrons. All right, that number is like 6 times 10 to the 19th power, or a 6 with 19 zeros after it. So it's this insanely big number. That's why we use an amp. All right, 1 amp is this crazy big number. So it makes it a little more manageable. All right. Now, current, resistance though, is the thing that slows down current. All right. You'll often see something like this. So now, if this, in this case, think of this as like water flowing down a pipe. That's a typical example because some of those properties kind of work with both things. All right. If all of a sudden I had a pipe, a large pipe, and then I had it go down to a small pipe, that would make, like a traffic jam, that would make all of a sudden now I have less electrons going down this than I have here. It's going to slow everything down, which in many cases is very good. All right. If you have too much current in a circuit, that's how you could have a light bulb go out. You could burn up a motor. All right. You need to manage the current and resistance balance between two things. And it's just as simple as looking on the box of that part. It'll tell you how much current can go to that part. If you look at a light bulb, it'll say you can only have 1.5 amps go through this. And so then you can balance your voltage and your resistance to make sure that your current is appropriate for that component. All right. Now, in the case of automotive, typically our resistance is the thing that is getting turned on by electricity. All right. So if this is a wire, and here I have a light bulb. All right. And so is what's going to happen as electricity comes down here. It's going to go into this light bulb. All right. And that light bulb is going to light up. It's using those electrons to light up. Well, right there, it's going to slow down the flow of electrons. This light bulb has a certain resistance. All right. It's built in. It's using electrons. Therefore, it has resistance there. So oftentimes, as long as we're using these electrons as we're going back to our battery, we should be okay. It's the same thing with a motor. All right. We have a blower motor for your AC, for example. I'm going to come in here, and I'm going to go out. This motor, the more electrons I have going into this motor, the faster it's going to spin. But by spinning, it's using up that energy. All right. And therefore now it's going to slow everything down. So now as that goes back to the battery, it's safely going back to the battery. The issue we typically have, we'll do a quick simple circuit here. All right. I have a battery, and this is a light bulb. All right, I have a battery and I have a light bulb here. Let's just say this is a AA battery, which is 1.5 volts. All right, 1.5 volts on that battery is going to push, it's my electrical pressure. It's going to push electrons through here, and it's going to light up that light bulb. That's going to get bright. All right. But by doing that, it's going to also slow down the electrons as they go back to the battery. All right. Remember, this is an electrical circuit. The word circuit derives from the word circle. Everything in terms of our automotive stuff, it's a little different on your house, but for automotive, everything has to go back to its source of power. All right. And we know this. For example, if I had a switch right here, this is a switch. All right. This is a switch. So right now the switch is open. I have an open circuit. Open circuit, that means electricity cannot flow. All right. Because right now it's coming around here. All right. It's coming around here. My light bulb is not on because I can't get back to my battery. I have no connection from this point to that point. All right, it's open by design with a switch. Now, once I close this switch, I have a closed circuit. Okay, I've now closed that switch. I've turned on my headlights or whatever we're doing here. All right, and now I can have electricity can flow all the way back to my battery. Therefore, that light bulb will turn on. Now, let's say in this example, I changed this battery and I put a 9-volt battery. 9-volt battery. All right. So now I've increased my voltage. I've increased my electrical pressure. All right. So now I can push more electrons through this circuit, all right? I can push more because I have more pressure there. My resistance hasn't changed. My resistance, it's the same light bulb. The resistance is a constant here, all right? It has not changed. Therefore, if I push 9 volts through this, I push more electrons, so we can expect this bulb just to be brighter, all right? It's getting more force there, and so it's going to be, multiple times brighter than it was previously. Now, you have to balance this stuff out, all right? I may buy this light bulb right here, or for example, let's say I put a 20-volt battery. All right, let's say I have 20 volts going through there. At some point, I'll be pushing so many electrons through that bulb, it's not providing enough resistance. And what will happen is this bulb will go out or burn out. All right, so there is a balance. You have to kind of balance your voltage with your current and your resistance to make sure that that could safely operate. And these are easy to find out. Most of the packages will have it. Your schematics for your vehicle will have the various ratings that they can have. And so we can define these things. It's not difficult, but it's something that we will need to do. Now, I don't want to get too much into the math on this, although it's not crazy mathematics. It's really not. But I think it's important that you guys see this relationship. All right? So there's a thing called Ohm's law. Ohm's law. Ohm's law states that voltage equals amperage times resistance. Voltage equals amperage times resistance. Now, with our vehicle, for the most part, our voltage is constant. All right? We're going to have right around 12 volts for most of our vehicles. So, let's say I'll go back and look at that light bulb. I'll take a look at that light bulb and it'll say, hey, that light bulb is rated for 1.5 amps. All right? So if I have 1.5 amps, so I don't know what my I have 1.5 amps. All right? And so based on this equation, I have 8 ohms of resistance in that light bulb. All right? That balances this equation. Now, if I decrease resistance, if I change it out for a different light bulb, if this goes down, if I had 12 volts, and let's say, for example, I had 3 amps, all right? If I had 3 amps, then my resistance would be 4. So as my amperage goes up, my resistance goes down, and vice versa. If I had 12 volts and I had 1 amp, I would have 12 ohms of resistance. So as my amperage goes down, my resistance goes up. So we can actually, based on looking at the component that we're putting into our system and understanding how many amps it requires to work, we'll know the resistance of that circuit and we can make sure that it's safe across the board. All right? So the main thing I want you to know from here is that these are like opposites. They're what's called inversely proportionate. All right? If this goes up, that has to go down. If this goes down, this is going to go up. All right? Now, we need resistance in a circuit. And here's why. All right? I'll go back to that battery example. Here's the symbol commonly used for a battery. There's many symbols in electrical. So I have battery here. All right? Here's my positive side of the battery, and this is 12 volts. I'm going to a light, and I'm coming back to my battery. All right? If something happened, so now I have current going through here, it's turning on my light bulb, it's a safe circuit. We've measured everything, we understand the amperage load that this bulb can take, all right? And we have enough resistance, so it's gonna be a safe circuit. If for some reason this light bulb was taken out of the equation and I had no resistance now, I have nothing that's called a load, I have nothing that's using the electrons, they're going to jam around here so fast, all right, it's actually going to heat up that wire. And in extreme cases, it can cause a fire. Usually it just heats up the wire. And you guys ever like bent a paperclip back and forth until it breaks? That's because have you ever felt that it's actually hot? You've created a lot of friction in there and then it actually breaks. Well, it's the same thing. Like if you rub your hands together a lot, they warm up, all right, and they get warm. Well, in case of a wire, if it gets too hot, it'll break, all right? And usually just kind of separates, which could cause a lot of other problems as well. But eventually they're going to go around so fast. Boom, you're going to go around so fast, these wires are all going to heat up. All right, and if they're next to something sensitive, that's going to heat up too. That could be a problem. But more likely, that wire is eventually going to break. It's going to open your circuit. It's going to stop the flow of electrons. Everything's going to get shut down. All right, that's not by design, right? This scenario right here, if we either have no resistance or not enough resistance, this is called a short circuit or a fault. A short circuit or a fault, all right? All right, guys. If you guys have any questions, please let me know. But just remember, we have 3 things that we can measure in a circuit. All right, we can measure voltage, we can measure current, we can measure resistance. All right, and we have to balance these things anytime we're working with electrical properties or components on our car to make sure that they're operating on what the manufacturer says that we have to put them in. And if they're not doing that, why? Why are we getting too many amps to that circuit? Something's wrong in our circuit. And so we're going to look at future lessons on how to diagnose what's causing this problem. And then hopefully we can isolate that problem and then take the steps to fix that problem. Okay, I hope this made sense to you guys. Let me know if you have any questions and we'll cover them in class. All right, take care.